Hello. Today our topic is sequential logic circuits. Before that, we have discussion about the combinational logic circuits, where you see that output depends only on the inputs. But in case of sequential circuits, the output depends upon the present input as well as past. So how we are going to store the past output so that memory element is that we see in this case we have memory element. So along with combinational circuits, we have memory elements here that is going to store the past output. And whenever we require, this past output is like. So this sequential circuit having two types. One is called as synchronous, another is called as the asynchronous. So in case of synchronous sequential circuit, here we have memory element that is being designed with the help of flip-flops. So we have slowly discussion about the flip-flop also. So in case of synchronous, we have clock cycles that clock, and we can have clock generators. So each and every flip-flop, if you see that later, that will connected with the same clock pulse. So it is also called as the clock sequential circuit, where same clock pulse is distributed to all and each and every segment of the flip-flops. So the output of the flip-flops either can be 1 or 0. And we know that flip-flop is the edge trigger device. So that discussion also we have depth in the later. So the sequential circuit block diagram, we have combinational circuit, and this is the memory element. So in place of, or you can say that memory element is designed here with the help of flip-flops. And whenever we have flip-flops, clock pulse is required. So this flip-flop can have positive transition, or we call this one as the positive edge trigger. So at whenever it's going to change from 0 to 1, then only flip-flop will be triggered. So that we can see here with the help of timing diagram. So next, another type we have asynchronous sequential circuit. So in case of asynchronous, we are going to use delay element as the memory. So where the propagation delay of the logic gates is going to provide the sufficient delay. So again, this delay can be controlled also. So again, depend upon the different time delay devices, we can have different delay also. So next is the latch. So latch name is the latch itself. So L is latch. So L for the level also. So latch is the level trigger device and it's going to store the 1 bit of the information. So here in case of asynchronous sequential circuit, if you see that we have discussion about this. So we have different types of the latches. So we have first one is the SR latch, as we call here for the set, R is the set. So these latches are the cross-coupled devices where output is connected to the input. So SR latch can be designed with the help of either NOR gate or NAND gate. So first we are going to see the SR latch with the help of NOR gate. So here if you see that one input to the each NOR gate is connected, that is the taken as here reset and set, and then output is here Q and Q bar. So that Q is connected to the input to the, if you will give the number here, this is NOR gate 1, this is the NOR gate 2. So this is the cross coupled output of the NOR gate 1 is connected to the input to the NOR gate 2, as well as Q bar is the output of the NOR gate 2, which is connected back to the input or to the NOR gate 1. So to understand the operation of this SR flip-flop with the help of NOR gate, we need to understand the truth table of the NOR gate. So here we have, this is the truth table of the NOR gate. So in case of NOR gate, if you'll observe that if any input is 1, if any input is high here, then output we are sure that output is 0. So this concept we are going to use here to understand the operation. So here we are taking here first combination where we have taken R as the 0 and S is taken as the 1. Now for the NOR gate 2, we are sure that its output is going to be the 0. Since why output is going to be 0? Since this is the basic property of the NOR gate that if any input is high, then output is the 0. Now this 0 is going to become the input to this NOR gate. So now finally both inputs are 0, 0. That output of this NOR gate 1 is the 1. So when Q is 1, then Q bar is 0. So both are complement of each other, or you can say that outputs are complementary. So Q is 1, so this will be called as the state. So this is the condition what we are taking. Now, if you are going to change here, like if you see in this case here, when we have S1 R0, Q is 1, Q bar is 0, this is called as the state. Now, if you are going to change here S to the 0, so when next condition we are taking that S is 0, R is already 0, that remain in the 0 condition. So now S is 0 and R is 0, what was earlier 0. Now S we have brought to the 0. Now both inputs are 0. So now we are going to take the help of the previous output. What is the, or you can say that what was the present output. On the basis of that, input has changed. So what will be the next output? What will be the next state that we are going to observe? So here, another input to the NOR gate is 0, since Q bar is 0 here. So now both inputs are 0. The output of the NOR gate 1 is what? 1. Now this 1 if you give back here to the input, to this NOR gate 2. So input combination becomes 1 and 0. So when we have 1, 0, that output of the NOR gate is what? 0. So what we are observing that device was in the state, it remained in the state only. Even we have changed S to 0. Similarly, if you see that when we have condition S is 0, R is 1, then in that condition, which NOR gates having one input as 1, that we are sure that output is going to be the 0. So on the basis of that, if you'll observe here again, that R is 1 and again S is 0. So since here for the NOR gate 1, one input is 1, so we are sure that this output is 0. Now 0 is coming here, and again we have already 0 here, so 0, 0, that output becomes 1. So now Q bar is 1 and Q is 0, this is called as the reset. Similarly, if we change R to 0, the device will remain in the reset condition. So there will be no change, it will be remain in the reset. So that's why when we have 0, 0, there is a no change. What was the previous condition, either set or reset at the reset. Now we have another combination when we have 1, 1. If both inputs are 1, then you are seeing that both NOR gate will have output 0. So that is called as here forbidden conditions. So normally that SR latch in default both inputs should be 0, 0. So that will be the condition. Later we see the function table. So there we are writing as the no change. So this is the operation of the SR latch with the help of NOR gate. Similarly, we have SR latch with the help of NAND gates. So if you see that in the previous one, if you will observe here, from where you are taking the output Q, that NOR gate is connected to the R, and from where we are taking the Q bar, from that input to the NOR gate is S. And in case of NAND gates, we are going to change here, from where we are taking the Q, that is connected with S, from where we are taking the Q bar, that is connected with R. Again, to understand the operation of this SR latch with NAND gates, again we need to know the truth table of the NAND gate. So this is the truth table of the NAND gate. So in case of NAND gates, what we are going to observe, if any one of the input is 0, we are sure that output is going to be 1. So this concept we are going to use here. So first situation, we are taking S as the 1 and R as the 0. Now if here if you mark again NAND gate 1, NAND gate 2. So in this case, NAND gate 2 in having one input as 0. So we are sure that this output is going to become 1. Now this 1 is going to be the input here. The one input is already as is 1. Another output Q bar is connected here to the input. So both inputs become 1, 1. So that output of the NAND gate should be 0. So now we got Q as the 0 and Q bar as the 1. So that is called as the reset. So now in this case, we are going to make the change that this R also we are trying to bring to the condition 1. So if you see that if you are going to make R as the 1, S was already 1. So that will maintain the same condition here. S remain as the 1. R we have changed from 0 to 1. So here now we are going to take the help of the previous output on the basis of that when we are going to discuss. So another input is here already to the NAND gate 1 is the 1. That is the previous or you can say that it is the present state. And after that, when this input will be applied, then next state is going to be different or it remains same that we are going to check. So now here both inputs become 1. So we know that output will be 0. So what we are seeing that what was the previous output, this output remains same. And here also again, if this 0 is given back here, so one input is 0, another input is 1. So that output remains the 1 here. So what was the previous state? It remain in the same state. So here in case of NAND gate, if both inputs are 1, 1, so there will be no change. What was the previous state? So in this case, it is the reset, so it remain in the reset. Whereas if you see that if S is 0 and R is 1, then we are going to get Q as 1 and Q bar as the 0. So this is called as the set. And again, if you are going to change the value of the S here to the 1, it will remain in the previous state, that it was set, it will remain the state. So whereas in case of NOR gates, what you are saying that when we have both was the 0, 0, then it was the no change. Whereas in case of NAND gates, when both are 1, 1, there is a no change. So NAND gates, by default condition, both inputs will be 1, 1 until we are not applying the data input. And in this case, when both inputs are 0, 0, I mean, if NAND gate 1 having input 0, NAND gate 2 also input 0, then we hear what will happen here. Both having one input as 0, then both output is going to become 1. So that is not acceptable. That will be called as the forbidden condition. So since all output is always high here, it's not going to change here since one input is 0 to the each NAND gate. Now this SR latch we can design with the help of control inputs also, where apart from the S and R inputs, we can control this one with the help of enable inputs. So here if you see that apart from the what was the cross coupled NAND latch earlier, one more NAND gates, you are seeing that this portion is added here and again one NAND gate here. Now if this one will mark as 1, this is the 2, so this will be the 3, this is the 4. So now we have set of 4 NAND gates we are going to use here. So again we can understand the operation. So here again we have concept of active low enable and active high enable. So suppose for example, when enable is 0, then we are going to get the desired output for which we are going to design the circuit. Then it will be called as the active low enable. And when n equals to 1, for that we are going to get the desired output. Then it will be called as the active high enable. So we have two different types are there. So generally here we are going to consider active high enable. So if you see the truth table here, when enable is 0, so that NAND gates 3 and 4 is not going to work here. So S and R both are cross here, and next state is what? No change. This one we can represent with the help of Pn plus 1, or we can represent with the help of Qt plus 1. Now when enable is 1, so that means both NAND gates 3 and 4, one input is 1. That we are sure about this. Now if S is 1 and R we are keeping as the 0, So for the NAND gates, both input is 0. So this is the output of NAND gate 3 is 0 here. Here one input is 1, another is 0. So that we are sure about this, that output is going to be 1 here. So now this NAND gate 1, one input is 0, and NAND gate 2, another input is 1. So now how we are going to decide? Again, what will be the output here? The same NAND gate concept we are going to use here. If any input is 0, output is 1. So now for the NAND gate 1 here, one input is 0. So we are sure that output is here 1. And this output is given here input. So finally 1, 1 is the input. So output is 0. So now Q is here 1, Q bar is 0. So that will be called here condition of the what we will call state. So whenever we have, if you see here, S is 1, R is 0, this is called as the state. And again, if you change the situation, similar way we can explain, when S is 0, R is 1, then here Q will be 0 and Q bar will be 1, that will be called as a reset. And whenever S and R both are 0, then there will be no change. It will maintain the same previous state. If device was set, it will remain in the state. If device was reset, it will remain in the reset. And when both S and R is 1 and enable is also 1, that is called as indeterminate states. So similarly, we have another type of the latch we call as the D latch. This is also called as the transparent latch, since whatever input we are going to give, that input will be available at the output also. So here we can have a small change in the SR latch, and we can have similar discussion for the D latch also. So since in the D latch we have only one input, so here if you see that in place of S and R, what we have given earlier, so D is connected to the S, whereas the complementary of the D, that is with the help of inverter, is connected to the R. So always S and R will not be equal. If S is 0, R will be 1. If S is 1, R will be 0. And here enable is 1, same as before. So if you see the situation here, so what is the, if D we are taking 0 here, so again we can mark here 1, 2, 3, 4. So for the NAND gate 1, one input is here 0. So we are, and another input enable is 1 here. So 0, 1 is the input. So what will be the output of the NAND gate? 1 is what? 1. Similarly here, one input to the NAND gate 2 is 1, another is 1. So both inputs are 1, so output is going to become 0. Now for the NAND gate 3, one input is available, that is 1 here. And for the NAND gate 4, one input is 0. So NAND gate 4, having since one input as 0, so we are sure that its output is going to become 1. And now this 1 is given back here as the input to the NAND gate 3. So both inputs are 1, so output is 0. So Q is 0. So what D was also 0, Q is also 0. So that is what is the input available at the D. Same output is available here at the Q. So that's why it is called as the transparent latch also. Once you reverse the condition, Q will be 1 and Q bar will be 1. So when D is 0, Q is 0. So this is called as the reset state. When D is 1, Q is 1, that is called as the state state. So for each and every latch here, we must have to understand the functional table on the basis of which it is going to work. So what we have discussed earlier about active low and active high, that concept is mentioned here. And these are the various symbols that we are going to use here for the SR latch or D latch. So later we can have a discussion about the flip-flops. Okay, so that or we can have a discussion now also, we can continue with this. So, but it is going to be a little bit lengthy topics. So maybe we try to conclude here, and later we can have discussion about the flip-flops. So in case of flip-flops, if you see that we have difference between latch and flip-flop, generally they used to ask. So in case of latch, it is the level trigger 1-bit storage device, whereas the flip-flop is the edge triggered 1-bit storage device. So again, we have different situation in case of flip-flops also, like we have positive edge transition, negative edge transition. So these are again we are going to discuss. So today we'll conclude with latches. Apart from this, we have D latch, SR latch, what we have seen already. Apart from this, we can have discussion about the JK latch and the T latch. T latch is called as the toggle. JK generally, again, we'll have later discussion where we can have discussion about the master slab also when we'll study about the flip flops. And later we can have again discussion about JK latch and T latch. So T for the toggle. So there you should see that Q and Q bar both are complementary of each other. So during the discussion of the flip flop itself, we'll try to include this concept of the latch also. Okay, thank you. Again, if any there are some other requirements are there, you can message me, you can do the comment so that we can make the video on that for the better preparation, for the better